I'll just give it a few more seconds, get a few more of you in, and then we'll start. Cool. Okay, so I think we'll begin. Hi everyone, my name is Preshayla. I'm a tutor at MyTutor, have been for about 2 to 3 years. I study physics at Loughborough University, and my favourite topic in physics is quantum mechanics. Fun fact. Hope everyone's really looking forward to Christmas despite COVID, but hopefully this is giving you a nice little break, an opportunity to still learn and keep things fresh in your head, especially if you're coming up to GCSEs this year. As you know, or may not know, these 3 webinars focus on what I think are 3 of the hardest topics in GCSE physics. So we've got electricity today, and we'll be having electromagnetism tomorrow, and nuclear physics the day after. So them 3 are probably the hardest in my opinion. So hopefully I can break it down for you, make things a little bit easier, a little bit simpler. We'll go through some practice questions, and what I tend to do is flick them up on the screen if we run out of time, so that no practice questions are left out, and then you guys can go away and do them in your own time. Okay, so let's get started. It's going to be quite a full-on session because electricity is a huge topic. So if at any time you need me to slow down, then please put that in the Q&A box. If you've got any questions, please also do put them in the Q&A box. I really want to hear your questions. And also I'll be asking questions throughout the session to you guys, just to try and keep it a little bit interactive. So the answers to those questions, could you please put in the chat box? I can see some Q&As already coming through saying, what exam board is this, and that kind of thing. So this is all for the AQA syllabus. So AQA, double, triple, I'm going to cover it all. The thing with physics is it's universal, right? So AQA, Edexcel, OCR, they have a lot of overlap. There will be slight differences, but today can focus on AQA. Sorry, I can't cater to everyone's syllabus, but this will give you a really, really good grounding anyway. Okay, so the first thing when we're approaching any topic in GCSE is to look at the syllabus. What do you actually need to know? So electricity, as I said, it's a huge topic, and you can kind of split it into 5 different subtopics. First one is the basics of electricity, so current, voltage and resistance, and how they behave and what their relationship is. We'll start by looking at circuit symbols. We'll look at electric charge and current. We'll look at current, potential difference in resistance, and then we'll look at resistors and how they behave and what are the different types. Then we're going to look at series and parallel circuits and what are the differences, maybe do a few calculations. Then we're going to look at domestic. So what is the electricity in our home? Where does it come from? What voltage is it? And how can we be safe when we use it? I think that bit's quite good because it's actually relevant. Energy transfers, so power, everyday appliances. We're going to look at how your kettle behaves, how your microwave behaves, which again is actually relevant. So I think it's really nice to keep it nice and relevant. Energy transfer equations and the national grid, which is how electricity gets around the UK. And finally, we're going to look at static electricity and electric fields. Cool. Okay, so these are all the topics in the electricity part. There are also some practicals, which we'll hopefully get time to do in the questions. And yeah, so let's start. So I've got some circuit symbols on the screen. These are the ones that you absolutely need to know. Any of them could come up. and in any combination. So we not only need to know what they are, we need to know how to draw them, we need to memorize them, and we need to be able to interpret them in a circuit. So when we have more than one component, what happens? How does current flow? So you guys can take some time maybe to just match these up in your head, have a think. Do I know these? Do any of these look really unfamiliar? Have I not even seen some of these before, which is absolutely fine. We're all different levels and all different years. So don't worry if you've not seen them or if you have no idea what the name means. We are going to go through it. But in your exam, this is all of them that you need to know. You won't see any others apart from these. So these are all jumbled up. See if you can, in your head, just match them together. Just have a think. Maybe think if any of them look unfamiliar. Maybe you don't know what one of them is. I'll give you a few seconds just to have a think. Okay, so hopefully you've had some time to have a look at these. I think the session is being recorded. Correct me if I'm wrong, Olivia. But if it is, then you guys can, what I hope you can do is pause the video and have a go at this at home for part of your revision. And these are the answers. So the first one is obviously our open switch and the second one is our closed switch. And then we have our cell and then we have our battery. So really important that we know the difference between them. The cell is just one, and battery has this dashed line in the middle to show that it's lots of different cells joined up to create the battery. The next one is the diode. The way that I like to remember what a diode is through the symbol. So you'll see that it's got an arrow pointing to the right. Diodes, by their nature, mean that current can only flow in one direction through the component. So in all the other components, we can have current flowing one way and the other way. But in diodes, we can only have it going through one way. Okay, and that's why that arrow is stopped off at one end. Then we have the resistor, really nice and simple. It's just a simple rectangle, comes up a lot, so one to watch out for. Next one is variable resistor, also comes up a lot, and it's a resistor, but just with an arrow through it to show that it does change. A light emitting diode, LED, that's what LED stands for, light emitting diode, is a diode. So you can see that we've got that same symbol, the diode symbol. And those two arrows that you see coming out of it are light. Okay, so it's light emitting diode, which is just an LED. You might have strip LEDs in your room. You've probably definitely seen an LED before. So that's what that symbol is referring to. Then we have the lamp, probably the most commonly used. In all our kind of circuit diagrams, we tend to have a lamp because it's a good indication of whether the circuit is on or off, right? If our lamp is on or if it's off, if it's brighter, if it's duller, there's a lot of different things we can do with the lamp. Then we have our fuse, our voltmeter, our ammeter, which measure voltage and current, and our thermistor and our light dependent resistor. Okay, so thermistor and light dependent resistor we're going to look at a little bit later, but these are the ones that you need to know how to recognize. Be careful not to get confused between the four rectangular ones: resistor, variable resistor, thermistor, and fuse. Very similar, but completely different things. Okay, let's have a look at, just going to check my Q&A. Cool. So electricity, this is a really, really simple circuit that most people will use to teach the basics of electricity. So we've got a battery can be a battery or a cell, doesn't really matter. There's a switch just to tell us whether our circuit is closed and complete, or whether it's open and it's not going to work. We've got our light bulb, again, just to bring a bit of practicality to it, and then our wires in between. So really, really simple circuit. And it's the best kind of circuit to understand how voltage and current work together. So you've probably heard of potential difference, voltage, current, charge. There's loads and loads of different things in electricity. And our job is to work out how they all work together. There's quite a lot of equations as well, and that's going to help us to determine these relationships. So how does electricity get round a circuit? What is it that lets the electricity from the battery get into the switch and into the light bulb and through the wires? What is making that electricity go round? Nobody's pushing it. How is it getting from one end of the battery around the circuit and back in? If anybody's got any ideas, I'd love to hear your thoughts. And if you could put them in the chat, that would be great so I can have a look. How does electricity actually get around the circuit? Electrons in a current, cool. The voltage pushes the current through, brilliant. Wants to go negative to positive, okay. Current, good, good. Electrons, it follows the current, brilliant. Loads of really, really great answers. Potential difference, good. So those of you saying that a potential difference provides the push are absolutely spot on. So we've got our battery, and in that battery, let's say we've got 6 volts, okay? My potential difference is 6 volts. That's what this bit means here. PD is 6 volts. So my battery is a 6-volt battery. Doesn't really mean anything if you just have a battery alone, right? You've got to connect it to something. Each of those volts is like a hand pushing, okay? That's how I want you to think of it. 1 volt is like a hand pushing. That volt pushes coulombs of charge around the circuit, or electrons, okay? So the voltage, these 6 volts are pushing the electrons around the circuit to allow electricity to flow. The only way that charge can flow around a circuit is if there is this potential difference. Without the potential difference, there's nothing pushing it, okay? It has to be pushed around the circuit. Now, charge, we know, goes around the circuit in the form of electrons. But what's current? How does current relate to charge, and how does charge relate to current? Well, current is the rate of flow of charge. Okay, current is the rate of flow of charge, which basically means how quickly are the coulombs moving around the circuit. A higher current, a higher rate of flow of charge. A lower current, a lower rate of flow of charge. So the coulombs, they're just not getting around the circuit quick enough. Okay. Current, again, is the same everywhere in a closed loop, which makes sense. We have 6 volts pushing all around the circuit, and that doesn't change. Okay, so let's have a look at our circuit. What does potential difference mean? Somebody's put in potential difference is voltage. Okay, they're the same thing. But in your exam, you want to be using potential difference. It's a really good key term, and it will actually help you to understand this positive and negative terminal. So in a battery, we have one positive and we have one negative. If they were both positive, that wouldn't be a potential difference. That would be potential same, right? They're both positive. There's no difference between them. There has to be that difference in order for charge to flow. Okay, which is why it's nice to use potential difference, just to remind yourself of the fact that there needs to be a difference in in those two terminals. So yes, potential difference should be used rather than voltage in an exam. Okay. And now you can see that I've got a potential difference of 6 volts, a current of 3 amps, and a resistance of 2 ohms. And for those eager-eyed of you, you'll know how they relate together. So current, charge, and time, we meet our first equation. Maybe you've seen this before, maybe you haven't. Don't worry if you haven't. This relates the charge that flows around the circuit. Okay, so charge flows around our circuit, and we know that the rate of flow of charge is current. Now, rate. I really want to talk to you guys about rate. Rate is a really, really important keyword in physics. Okay, does anybody know what rate means? When we see rate in a circuit, what does that refer to? What is the meaning of rate? It comes up so much in physics, but what's its meaning? What is the meaning of rate? How fast something is, good. The amount of times it happens, speed, time taken. Good, good, good. All really great answers. Okay, so rate is the measure of something over time. Okay, so it could be charge over time. It could be distance over time, which you guys know is speed. It could be energy over time. It could be energy transferred over time. It could be work done over time. Okay, there's lots of different things that we can put over time. Okay, so it's some quantity over time. Whenever we have this divided by time, whenever something is divided by time, that's its rate. Okay, so I want you guys, when you're looking at your physics equations, if you see time in there, that is the rate of doing something. Now, for those eager-eyed of you, you'll notice that we can actually rearrange this equation to show that current is the rate of flow of charge. So if I divide both sides by time, what I end up with is charge flow divided by time equals current. Okay, and there you see that we have our quantity over time, and that's the rate of charge of flow. Okay, so current is the rate of charge flow. We've got to be really careful to watch out for those. So coulombs, what are coulombs? Coulombs are the unit of charge, but amps are the unit of current. Current is definitely not the same thing as charge, and you've got to make sure to differentiate between the two with their units. Okay, going back to our simple circuit, let's look a bit more in depth about how current, voltage, and resistance work together. So we already know that we've got 6 volts, which is providing this pushing force to push electrons around the circuit and create a closed loop and allow electricity to flow. But the current that flows through a circuit, we can't set. We cannot set the current. We can change the voltage. We can do a different battery. We can do a different cell. We can take a cell away, we can add a cell in, we can change the voltage. That's easy. Yeah, we can put a 10-volt battery, we could put a 6-volt battery. Easy to do. We can also change the resistance. We can put a higher resistance light bulb in or a lower resistance light bulb in. We could put a light dependent resistor, we could put a thermistor, we could put a resistor, we could put a variable resistor. There's loads of different ways to change the resistance. But what we can't change necessarily is the current. I can't go and put a component in and set the current to whatever I want. That's not a thing. The only way to control the current is by changing the voltage or by changing the resistance. Okay, hopefully that's making sense. Changing the voltage is going to change the current in some way, which we're going to look at in a second. And changing the resistance is also going to have a knock-on effect on the current. So what's that equation? Think back to school, think back to when you did electricity. What is that equation that describes the relationship between current, voltage, and resistance? What is that equation? And if you know the equation, how does changing voltage affect current and how does changing resistance affect current? You can change both at the same time. You can change just one. Either way, you're going to change the current. Cool. Lots of you already know the equation, which is brilliant. It's the most famous equation in electricity, and it's the one that you're going to be using the most. So well done if you know it already. Does anyone know the alternative name for it? Maybe you can put that in the chat. Yes, it's V equals IR, but what's its actual proper name? Who came up with it? Okay, cool. So potential difference, resistance, and current are all related by this equation V equals IR, where V is potential difference. I know it doesn't make sense. It should be P or it should be PD. Just try to get your head around the fact that V stands for potential difference and not voltage, although they are the same thing. I stands for current. Again, it doesn't make any sense. It should be a C, but I stands for current, and R, that's a good one. It stands for resistance. Okay, so V equals IR is potential difference equals current times by resistance. And that's how they are related. Now, if we change one, we already know that we're going to change current. Yeah, if we change potential difference, we change current. And if we change resistance, we change current. So if I increase my voltage, what happens to my current? What happens? If I double my potential difference, what's going to happen to my current? Assuming that resistance is kept the same. What do we think? If I double potential difference, what happens to current? Maybe you'd like to fill in some numbers to test it out and see. What do we think? If I double potential difference, what needs to happen to current? Let's have a look. What do we think? Put your answers in the chats. Cool. It doubles. It's proportional. It will definitely increase. But what's really special is that it's also going to double. Okay, so if we double potential difference, there's this really cool phenomenon that means that we also double current. And that's because they're proportional to each other. Okay, this proportional, this keyword proportional, means that if you do something to one thing, the exact same thing happens to the other. So if I double potential difference, I double current. It's quite good, really, because we don't have to do too much maths. We know that it increases, but actually it doubles. Yeah, it's not just a random increase, it does the exact same thing. Okay, so we know if we double potential difference, we double current. But what happens if we double resistance? What happens to current if we double the resistance? Assuming that potential difference is kept the same, what happens? What happens? Put your answers in the chat. What happens if I double my resistance? Let's have a look. What we're thinking. What we're thinking. Cool. Good, looking good. Good answers. Oh, great. It halves. Brilliant. Okay, so if I double my resistance, my current is going to halve. So it's kind of the opposite. If I double my resistance, my current halves, which kind of makes sense. If we think about what resistance actually is, resistance is the opposition to current, right? Resistance is literally a component saying, no, we don't want this amount of current to come through. We're going to resist some of you. Okay, we're going to resist. That's too much for us. That's too much current. We're going to resist some of it, which makes sense. If we double the resistance, if we put even more resistance into the circuit, then of course less current is going to be allowed to go through because that component is resisting it. It's not allowing it to go through. Yeah. So if we double potential difference, we double current. And if we double resistance, we halve current. And that's a proportional and an inversely proportional relationship. Okay, doing really, really good so far, guys. And hopefully these basics are going to create a whole new kind of level of understanding for you. So I've got 4 questions on the board, the screen, whatever. Can you have a go at answering these? Feel free to put your answers in the chat, do them in your head, or multiple choice. Let's have a think. Cool. Some of you put in your answers. Guys, if you could put your answers in the chat box and your questions in the Q&A, that will really help me out. I'm going to answer a few questions while you guys are answering. Is it ohm proportional if it's an ohmic conductor? Yes, we're going to look at that in a second. Good. Do you mind defining charge? Yes, charge is the flow of electrons. That's really all it is. Charge is literally just electrons. Someone saying, what does I equals 3A stand for? That's current equals 3 amps. I is current, remember. Cool. Right, let's go through them. Don't worry if you've not had a chance to answer. You can pause the video when you watch it back and have a go. What is a flow of charged particles called? That's the current. Current is the flow of charge or the rate of flow of charge. What unit is charge measured in? That's coulombs. Charge is in coulombs, not in amps. Current is amps. Okay, really, really important that we don't. A lot of people tend to ignore coulombs, actually. People kind of forget about it as a unit, which kind of makes sense. It's a bit irrelevant, but you know, it's there, and that's the unit for charge. What current flows if 10 coulombs flow past a point in 2 minutes? So you're going to do 10 divided by 2, but minutes is the key bit here that I want you to recognize. We don't do minutes. Minutes just doesn't really work for us. We've got to change that into seconds. Okay, so when you change 2 minutes into seconds, you should obviously get 120 seconds, and then you do 10 divided by 120, which is 0.083. So maybe you got 5 amps, which is a little bit wrong. You should have got 0.083. So that's 10 divided by 2 times 60. Okay, that's what you should have got. So don't worry if you didn't convert it into minutes, convert it into seconds, now you know. And what is potential difference, also called voltage, but not in an exam. We want to be using potential difference. Okay, resistors, next kind of mini topic. Resistors are important. They allow only a certain amount of current through and they resist the rest. Sometimes in a component, resistance never changes. It's the same the whole way through the experiment for that component and it never changes. And that's good. We like that. It's really nice and simple. That's the basic case. But sometimes it does change and it changes as current changes. Okay, so sometimes it's constant and sometimes it changes. And if it does change, it's a dependency on current. So if current is changing, then resistance can also change. Now, this behavior, how resistance changes or doesn't change, can be shown on a graph. Okay, the graph is a plot of current against potential difference. And what's really important here is current and potential difference don't necessarily need to be on the y and the x. They can be switched around. And sometimes examiners or the people who set the exams are sneaky and they put V on the Y and current on the X. Okay, they switch and change them. It will look maybe different from your textbook. So we've got to be really careful to look at the axis first and then draw our graph. The ones that I'm going to show you are with current on the Y, but if you just kind of switch it around, you'll be able to see what it's like if you switch the quantities around. So we represent resistor behavior and resistance with current potential difference graphs. The straight line means that resistance doesn't change. It's the really basic, simple case. The resistance of the resistor doesn't change. And it's called, when this happens, an ohmic conductor. It follows Ohm's law. Yeah, everything's really nice and proportional. Everything's straight. It's a constant temperature, it's an ohmic conductor, and it follows Ohm's law perfectly. So resistance is constant, even though current is changing. So that's our basic case. Let me just check that nobody's got any questions. Okay. So that is actually really rare, unfortunately. That resistance not changing is quite rare. Okay, because in real life, things heat up. When things heat up, that can change resistance. So Ohm's law is kind of the perfect case, but actually there's all these different components that don't really have a constant resistance. These components and the ones that you need to know are lamps, diodes, thermistors, and LDRs or light dependent resistors. They're the 4 cases that don't have resistance being constant. They have resistance changing. Okay, and it changes as current changes. Okay, so the first one out of 4 is the filament lamp. The filament lamp. It's got this weird kind of S-shaped graph. So it's pretty similar to the Ohm's law case, the nice basic proportional perfect case, but it's got that kind of curving at the ends. Okay, and that's a filament lamp, and it's all to do with temperature. So as the temperature of the filament increases, the resistance of the lamp also increases. Okay, so as the temperature increases, the resistance also increases. Second case is our diode. So as I said in the beginning, the diode is a component in which current is only allowed to flow in one direction. And the way that they do that is that in the other direction, they make a really, really high resistance. And so current can't flow because it's such a high resistance. In the forward direction, it's all good, current can flow. In the opposite direction, there's a really high resistance, which means that current can't flow. And it looks like this. It's basically a flat line and then it shoots up when current is allowed to flow. Okay, and that's how the diode works. And then we have cases 3 and 4, which aren't perfect and resistance does change, are the light dependent resistors and the temperature dependent resistors, also known as LDRs and thermistors. So these are components where if light changes or temperature changes, then resistance is also going to change. The relationship is as follows. The resistance of a thermistor decreases as the temperature increases, and the resistance of an LDR also decreases as light intensity increases. And just to make it nice and relevant and practical, this happens in real life, right? We see it around us. The resistance of thermistor decreases as the temperature increases, and we see that in our thermostats at home. The resistance of an LDR decreases as light intensity increases in our phone screen. So maybe we go into a dark room and and your phone becomes brighter so you can see it, or vice versa. That works with light dependent resistors. Okay, so that's the end of our first topic. There's so many good questions and I will try to get to them all. But let's move on to series and parallel. So series is a closed loop, right? It's a really, really nice, simple case. It's just all the components are basically next to each other. And what's important to realize in series is that current is the same everywhere. So it doesn't matter if we're at the top, if we're just before the resistor, if we're just after it, current is the same everywhere. Okay, it's IT everywhere. The total potential difference, however, the potential difference in a series circuit is shared between the components. So this might have 3 volts and this might have 2 volts. The voltage is shared between the components. Current is the same, voltage is shared. And the resistance adds up. So if this resistor is 2 ohms and this resistor is 3 ohms, then they add together to give 5 ohms. Okay, so the total voltage is the voltage of one component plus the voltage of the other component, and the total resistance is the resistance of one component plus the resistance of the other component. And then it's the complete opposite in parallel. So this time, potential difference is the same everywhere. The voltage that comes from the battery is the same voltage that goes through this component, which is the same voltage that goes through this component. But this time, the current is shared. Okay, the current is shared this time. Current through this component adds with this component to give the total current in the circuit. So this time, potential difference is the same, but current is different and it adds. We don't need to worry too much about resistance in parallel. You won't ever have to calculate it, but the total resistance of 2 resistors in parallel is actually less than the resistance of the smallest individual resistor. Okay, so let me quickly give you an example of that. All I'm going to do here is I'm going to tell you that this resistor is 2 ohms and this resistor at the bottom is 3 ohms. When we combine the resistance of both of those resistors, what we find is that actually the total resistance in the circuit is less than 2 ohms. There's some weird maths that goes on there, which luckily you don't have to know about. But what you do need to know is that the total resistance of the circuit is actually less than the smallest resistor, which is really, really different to in series, where if you add more resistors, the resistance just keeps getting higher and higher. Okay. So they are basically opposite in every single way. And a really common exam question is to compare series and parallel circuits. What are the differences? What are the similarities? Yeah, okay. So let's have a really quick practice question. Let's say that the voltage in our circuit with potential difference, is 6 volts. And let's say that one of my resistors is 2 ohms. Okay, it's type 3 ohms for some reason, so it's 3 ohms now. And this one is, let's say, 3 ohms as well. Okay, so first of all, we need to work out the total resistance in the circuit. To work out the total resistance, we use this equation here, which is basically just add up the resistors and then you get the total resistance. So our total resistance is 3 ohms plus 3 ohms, which gives us 6 ohms. Okay, so the total resistance of our circuit is 6 ohms. That's our first step. Just put it there. And then we can put it into V equals IR. We can only use V equals IR when we have the total resistance. Okay, so V equals IR. We're trying to find the current, so we do I equals V over R, and so I equals our 6 volts divided by our 6 ohms, which is 1 amp. Really common exam question, probably 2 or 3 marks, but it involves you kind of having to do 2 steps where you find the total resistance first and then you do V equals IR. That's series and parallel circuits. And if you guys have any questions, I can have a look now. Some of you putting the answers on, which is great. Okay, now let's move on to domestic electricity. So domestic electricity is all to do with the electricity in your home, and it comes from this idea of having DC and AC. I'm sure you've all heard of the band AC/DC. It comes from there. So it's 2 different types of electricity, basically. One is DC, which is direct potential difference, and one is alternating potential difference. DC, we find it in car batteries and in solar cells, basically anything that has a battery or a cell. So my phone has a battery in it, portable chargers have batteries, a lot of things have batteries, right? And alternating potential difference is what comes through our sockets. So when we plug a socket, we plug a plug into a socket, that's AC coming through. Then gets converted into DC and goes into the battery of your phone. But AC is what is coming out of our sockets. Okay, now AC is what is being produced in power stations, which is why it comes into our homes as AC. And the reason that it actually happens to be AC is because it's made by magnets. In the UK, the electricity is at 230 volts. So the voltage that is coming out of your sockets is 230 volts and the frequency is 50 hertz. Don't worry too much about the frequency for now. We're going to look at that tomorrow. So here is what they look like. Here's what we kind of picture them as. AC is this blue wavy line because it's constantly alternating between positive and negative, positive and negative, and that's how we show it. DC is the red line, which just stays at one constant value the entire time. So DC is what is in batteries and cells, and AC is constantly changing and switching. We can convert one into the other as well. So this is where it gets really nice and relevant. Well, we actually look at what's in a plug. You've probably never even thought about what's in your plug before. You just plug it in and it charges your phone and we're all happy. But we do need to know about it because actually maybe when you have your own home, you might need to know this and you definitely need to be safe. So This is what it looks like inside. You're going to have 3 different wires and they're colored differently so that we know exactly which one's which. The blue is called the neutral wire, the earth is the green and yellow, and the brown is the live wire. Okay, that absolutely has to be remembered. Maybe you remember it because green is like the earth, grass, I don't know, it's a bit of a stretch. Neutral is blue, and live is, yeah, brown. Maybe that should be earth, I don't know. However you want to remember it, there's 3 different colors. There's a cable grip, which keeps all the cables together. There's a fuse. Fuse is basically just a component which, when current gets too high, it melts and it breaks the circuit. So if current is maybe supposed to be 5 amps, but it somehow gets 7, that fuse blows and it kills the plug. Okay, so sometimes maybe your hairdryer stopped working. That's probably the fuse is blown because the current has got too high. There's been a surge. So it's a nice protective feature. And then the outer insulation, which again is a nice protective feature. So loads of things to protect us in here. And we need to know the features and functions of them. So the outer insulation keeps it all together. And the plastic is obviously an insulator, so it doesn't allow the electricity to come to us. Cable grip holds them all together. The live wire is a copper wire, which is coated in brown, which allows electricity to actually flow through. So the live wire is, it's really the one doing all the work. It's the one that carries the electricity at 230 volts. It's the one that is actually going to charge your phone. The fuse, as I've already said, is a glass or ceramic little canister, about that tiny, like that big, which will melt if the current gets too high. Neutral wire, it doesn't really do much. It's held at 0 volts and it just basically completes the circuit. The earth wire is, again, another safety feature. And the earth wire provides this path for electricity to flow through if there's a surge. If there's a fault in the plug, the earth wire will take all the electricity and suck it out and push it down into the ground so that it doesn't harm us. Okay, power. Power is another thing that we need to look at in circuits. And power is, it has 2 equations that people use, which is power equals potential difference times current, and power equals I squared R. So that's power equals current squared times resistance. You can use one or the other, just depends on what information you have in the question. And power is measured in watts. Questions luckily don't tend to get too hard for power because it just tends to be, they give you the voltage, they give you the current, and you times it together. But what we do definitely need to know about power is that it relates to energy. So power is the rate of energy transfer, which we get from this left equation here. Remember, if we divide energy by time, we have the rate of energy transfer, which is equal to power. There's 2 equations for energy in an electric circuit, and it again just depends on what information you have. You can either use power times time, or you can use energy equals charge times potential difference. Energy is transferred all around us, usually in our kitchens, in our TV, definitely in our kettles, in our microwaves, and we need to actually know how our kettles and our microwaves work. So maybe on your microwave, you've seen that it's 800 watts, 900 watts, 1000 watts, whatever it happens to be. If your microwave says 800 watts, basically what that means is that it transfers 800 joules of energy every second from one store into another, which in a microwave would be electrical energy into heat energy. Okay, so a power rating of 800 watts, 900 watts, whatever, is that amount of joules per second. Okay, so you can see some here that I've put for you. So clock is 10 watts. Obviously a clock doesn't need a lot of power to run, so it only transfers 10 joules. per second. But an electric oven is, I actually can't see that. A kettle is 2,400. Okay, so obviously a kettle is going to need lots more energy per second to do what it needs to do than a clock. And that's called power ratings. And it's all done with this energy equals power times time equation. So domestic appliances transfer energy from batteries or AC, depending on what you plug it into, to the kinetic energy of electric motors or to the energy of heating devices. The national grid. The national grid is how we get electricity into our homes. So it's this combination of cables and pylons and power stations, which all fit together to provide us with electricity. So what happens is we have the power station, then we have a step-up transformer. The step-up transformer takes the power from the power station and increases the voltage of it and puts it through the lines. The voltage goes through the lines and goes into a step-down transformer, which decreases the voltage, ready for our homes. I'm not going to spend too much time on this because we're going to go through transformers tomorrow when we do electromagnetism, but this is basically how the national grid works. It takes transformers and it puts voltage through them and it pumps it into our homes. Okay, and the last topic, static electricity. So static electricity happens when we rub two certain insulating materials together. So you might have done the balloon on your hair, the balloon on a wall, your feet on the carpet, your socks on the carpet. That's all static electricity. So when two certain insulating materials are rubbed against each other, they become electrically charged. And this is because of the transfer of negatively charged electrons being passed from one to the other. The material that gains electrons becomes negatively charged, and the material that loses electrons becomes equally positively charged. That's what creates static electricity. It's that transfer of electrons. If there's no electrons being transferred between two materials, which is often the case, then there's no static electricity. It's when we start rubbing two materials together like a balloon on our hair that we have the transfer of electrons and therefore we feel static electricity. It's the same thing when we bring two electrically charged objects close to each other. You probably haven't done this too much, but it's really, really similar to when you bring two north poles together, two south poles together, or a north and a south pole together. It's the exact same thing, but just with electrically charged objects rather than magnetic objects. So if we have two charges which have the same type of charge, so two negatives or two positives, they're going to repel. Remember, like charges repel, just like poles repel. If they're different, they're going to attract. So opposite charges attract the same way as opposite poles attract. That's all you need to know about it. They don't need to be touching to feel this force. If you even bring them this close together, they're going to start repelling. Yeah? Or if you bring them close together and they're attracted to each other, they're going to start attracting from here. And that's what we call a non-contact force. They don't need to touch each other to feel this force. And finally, electric fields. So electric fields are when we have a charged object, it creates an electric field around itself. Okay, so we have a charge and we have an electric field around it. It does this by itself, it creates it by itself. And it's closer when we're really close to the charge, and it gets weaker and weaker as it spreads out. These black arrows, they're called field lines. And around a spherical charge, they are equal in distance and spaced apart. If it's a positive charge, they go out, and if it's a negative charge, they come in. And that's it. That is the entirety of electricity, guys. I know it's been a bit of a rush, but I really wanted to get through it all for you. And hopefully this is recorded and you guys can go back and watch bits. And yeah, so what I'm going to do is, while I answer your questions, I'm going to put example questions up on the board for you guys to have a go at later on when you're watching this back. And at the end of tomorrow's session, I'm going to put the answers and work solutions on the slide, so that again you can pause the video and check if you've done them right. It's just a really nice way for me to be able to give you example questions without having to spend too much time on them. So I'm going to put them up on the screen and you guys can pause the video. So let's have a look at your Q&As. They're going to load. I can't see them. Okay, there's something wrong with my laptop, which means I can't see the Q&As. Livia, are you able to send some in the chat to me? I can't see the Q&As. This is one of the required practicals in electricity. So it's literally just looking at a circuit, and maybe you have an ammeter in there, maybe you have a voltmeter, and you're investigating the relationship. You're investigating V equals IR. Okay, so when we change voltage, what happens to resistance? When we change resistance, what happens to current? That is the main required practical. So you've got to be really clued up on how they behave. Okay, so this is part of the required practical. So you've got your battery, you've got your ammeter, you've got your voltmeter, you've got your lamp, and you've got a variable resistor. So you've got to describe how the student could use her circuit to investigate how the current for a filament lamp affects its resistance. So what you would do here is, we want to investigate how current changes resistance. Yeah, so we're going to change our certain elements of the circuit to see how that changes current and how it changes voltage. The way that we change it is through the variable resistor. So as we vary resistance, what happens to current and what is the voltage? Okay, so what you would do is you would change the resistance, take the current reading, change your resistance, take another current reading, and investigate that relationship. Again, same thing. The experiment can be done by switching out this resistor for anything. It could be a light dependent resistor, it could be a thermistor, it could be any of those. And you've got to investigate the relationship. The reason that I'm putting these on the screen, guys, is so that you can pause the video and try them at home, because I don't want you to go away with no example questions to try. Okay, so I think that brings us to the end of the session. Thank you guys so much for attending, and hopefully I'll see you all tomorrow for electromagnetism. We'll be covering some of the same topics, such as transformers, and certainly a lot more new topics, trying to clear up some of the complexities there. Hopefully you guys can have a go at these questions as well, and I'll provide you with the answers at the end of tomorrow's session. So you can check them against the work solutions. Thank you so much for attending. Have a lovely evening, and I'll see you tomorrow.